Namaskar. Hello everyone. Stay safe, stay healthy and stay connected. So let's start with a new chapter today, that is work, energy, power, collision. In this we have to first of all start with what do you understand by work done. And work can be done by applying a constant force or by applying a variable force. So whenever you are doing work by applying a constant force, then work done is defined as that component of force which lies in the direction of displacement into displacement. So that component of force which lies in the direction of displacement is F cos theta into displacement is S. So it is Fs cos theta, which can be written as F dot S. So work done can be defined as the dot product of force and displacement. So if you are applying a constant force, then the graph between force and displacement will be something like this. And here for displacement S, let us suppose this is the force which is constant in nature. Then we can see that area under force displacement graph gives us work done. Similarly, if we have a variable force, and the force is something like this, which is increasing with displacement in a non-uniform manner, and we would like to identify work done till displacement S, then area under force displacement graph gives us work done. So if we have a constant force, then also if we have a variable force, then also work done is dot product of force and displacement. Now there are two cases, positive work done and negative work done. If the angle is greater than 0 and less than 90, then work done will be positive, and if your angle is greater than 90 and less than 270, because you know that cos 270 is -1, then work done will be negative. And zero work done cases, there are three possibilities for zero work done. One is when there is a force, there is a displacement, but the angle between them is 90 degree. Second is when there is no force, a body is moving with uniform velocity, then also work done is zero. And the third case, when there is no displacement, even though you are applying force on a body, then also work done is zero. So zero work done, three cases: when angle between force and displacement is 90 degree, when force is zero but there is a displacement, it means the body is moving with uniform velocity, then also work done is zero. And if you are applying force but there is no displacement, then also work done is zero. So work is said to be done if there is a component of force in the direction of displacement. Now there is a term which is called as kinetic energy, which is defined as the energy possessed by a body by virtue of its motion. It doesn't matter how the body has acquired that velocity, whether by applying constant force or by applying variable force. What matters is what is the velocity at a particular instant, then the kinetic energy at that instant will be given by half mv square. How to obtain that? For example, there is a block of mass m on which force F is applied, which produces a displacement S. Since the force is constant, so according to Newton's second law, acceleration is uniform, and we know that for uniform accelerated motion we can use equations of motion. And here we are assuming that the body was initially at rest, and after covering a displacement S, it acquired speed v. Now what will happen? Work done is as per the formula force into displacement, and the angle between force and displacement here is 0. Force is mass into acceleration into displacement. Now we know that since the acceleration is uniform, we can use equations of motion. V square minus u square is 2as. Since u is 0, so v square is 2as, so as is v square by 2. On substituting the value of as over here, what we are going to obtain is half mv square. So kinetic energy is half mv square, whether the force is constant or variable. For variable, let's prove it. Let us suppose a body of mass m is acted by a force F at any instant while moving from this position to this position, which produces a small displacement dx. Then work done will be integration of f dx. Whenever non-uniform force is there, then work done will be given by integration of f ds. Here also work done will be given by integration of f dx. Whenever constant force is there, then work done is force into displacement. Now here we know that force is non-uniform, so which can be written as m dv by dt at any instant into dx. We know that this dx by dt can be replaced as v, rate of change of displacement, and now we have to integrate it from 0 to v, so mass can be taken out. Integration of v to the power 1 will be v square by 2. Again we have obtained the same expression. So it doesn't matter whether the body has been acted by a constant force or a variable force, the kinetic energy will be half mv square at any instant, which can again be rewritten as, once you multiply this expression by m and divide it with m, this will be mv whole square by 2m, which is momentum square by 2m. So again kinetic energy is p square by 2m. Here you may get some numerical. For example, if the momentum of a body is increased by 100% or increased to 300%, what will be the percentage change in kinetic energy? And you very well know that how to calculate percentage change in kinetic energy. Change in value upon original value into 100. So first of all you have to find out kinetic energy at momentum p, then new kinetic energy at new momentum, then change in value upon original value into 100 will gives you the percentage change in the value of kinetic energy. Now what do you understand by potential energy? If there is a block of mass m and you are lifting it up to height h, let us suppose this height is h, and you are applying a force which is equal to weight, then potential energy will be force into displacement, so that will be Fh cos 0. Force here that you are applying is mg, so potential energy is mgh. So here potential energy is mgh. So this work, zero work done cases, negative work done cases, positive work done cases, then kinetic energy by constant force, by variable force, it doesn't matter. Kinetic energy at a particular velocity will be given by half mv square. Potential energy is mgh. Now what do you understand by power? It is defined as rate of doing work, which is having SI unit joule per second or watt. Instantaneous power means power at any instant is given by rate of doing work, means dw by dt. Now you can write this work done as force dot dx, force into displacement. Now again you can replace this dx by dt as velocity. So new formula for calculating power is dot product of force and velocity. So now these are the basic fundamentals of this chapter, based on which you are going to solve some numericals, and definitely we are also going to solve some numericals. Before that, let's wind up collision and then we can start with numericals in the next video. So this is our lecture 1 of work energy power collision. So now onwards we'll have one lecture based on the basic concepts and next lecture based on the numerical version of that chapter. And the third thing is, I'm going to send you some assignments on the same. You have to solve it, and if you have any queries, then we are going to have video session in which we can interact with each other through Hangouts. I hope you might have joined Hangouts as well. So let's continue with collision. In collision we have elastic collision and inelastic collision. Here momentum as well as kinetic energy both remains conserved. And if momentum is conserved but kinetic energy is not conserved, then that type of collision is called as inelastic collision. Kinetic energy is not conserved. Now in this collision, what happens if we are dealing in 1D, then elastic collision in 1D. Here if we have two masses m1 moving with initial velocity u1 in a straight line, m2 moving with initial velocity u2, they collide, and after collision their velocities becomes v1 and v2. Then what will happen in elastic collision in 1D, that if you conserve momentum m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, you can also conserve the expression for kinetic energy, which is half m1 u1 square plus half m2 u2 square. This is the kinetic energy before collision. That will be equal to kinetic energy after collision. And by solving these two equations, you can get the velocities of the bodies after collision, which you can easily remember as u1 u2, u1 u2. In the denominator, everywhere you are going to get the sum of the two masses, m1 plus m2, m1 plus m2. Here v1, so here you will get m1 minus m2 here, and here 2m2. Here v2 is here, so you are going to get m2 minus m1, and here 2m1. So using these two equations, you can get the velocities of the bodies after collision if the collision is elastic. If the collision is elastic. Now instead of elastic collision in 1D, if you are going to have it in 2D, then since momentum is a vector quantity, you have to conserve it component wise or in vector way, and kinetic energy is a scalar quantity, so you can use the expression for kinetic energy directly whether it's 1D or 2D. So here if 2D, what will happen, let us suppose mass m1 is moving with initial velocity u2, it collides with another mass moving with initial velocity u2, and after collision m1 starts moving with velocity v1 at an angle theta 1 and m2 starts moving with velocity v2 at an angle theta 2. Then what we are going to do is we have to break this into components. Let us suppose x-axis, we have to conserve momentum, which is m1 u1 plus m2 u2, that is m1 v1 cos theta 1, the component of m1 momentum along x-axis, then m2 v2 cos theta 2. If you are dealing with y-axis, then initially it was 0 before collision, and after collision the momentum of m1 towards y-axis is m1 v1 sin theta 1, and it is downward, so it will be minus m2 v2 sin theta 2. Now there is one more term which is called as coefficient of restitution. Coefficient of restitution, which is defined as, it is defined as the relative velocity of separation, ratio of relative velocity of separation to the relative velocity of approach, because once you solve these two equations, you are going to obtain that relative velocity of separation is same as relative velocity of approach in elastic collision in one dimension. Coefficient of restitution is defined as the ratio of velocity of separation to the velocity of approach, and if its value is 1, then it is elastic collision. If its value is 0, then it is called as perfectly inelastic collision. Means after collision both the bodies will stick together and will move together. So that is called as perfectly inelastic collision. Here v2 will be equal to v1, and if E is greater than 0 and less than 1, then it is called as inelastic collision. So in this chapter, work, energy, power and collision, what do you understand by work? Work is said to be done if there is a component of force in the direction of displacement. There could be positive work, there could be negative work, there could be zero work done. Area under force displacement graph always gives you work done. Constant force, variable force, it doesn't matter. Area under force displacement graph gives us work done. Then kinetic energy possessed by a body by virtue of its motion, which is half mv square, which is p square by 2m square. Potential energy is mgh. Power is defined as dot product of force and displacement or rate of doing work, which is having SI unit watt. Collision is said to have occurred when the two bodies physically collides with each other or when the motion of one gets affected by the other. In collision, you have two types of collision, elastic collision, inelastic collision. When momentum and kinetic energy both remains conserved, then it is called as elastic collision. When momentum is conserved but kinetic energy is not conserved, then it is called as inelastic collision. Elastic collision in 1D, you observe that relative velocity of approach will always be equal to relative velocity of separation, whereas in inelastic collision, what you have to do is you have to just use the expression for momentum conservation. Kinetic energy will not get conserved. You can easily calculate the loss in kinetic energy by calculating initial kinetic energy minus final kinetic energy. That will be the loss in kinetic energy while in elastic collision. When two bodies after collision stick together and move together, then that is called as perfectly inelastic collision. Now here in lecture 2 we are going to solve some numericals, so just revise these concepts. I am going to send certain notes to you as well. Just go through the notes, revise it, and stay safe, stay healthy and stay connected.